All right, number one, could you do number one? Everybody?
Yep.
You okay with number one?
So basically, number one, all we were doing is just multiplying them together, correct? If I can have force?
Yes.
Okay.
But remember, force and acceleration, net force and acceleration are always related. Okay, always. So if you have a net force on an object, you must have an acceleration. All right, and that's the formula you would use to calculate it. And the heavier it is, the more massive it is, and of course, that will change how much one affects the other. But yes, that's right. What about number 5? You guys are okay with that, number 5?
Yes, 0.00005.
Okay, or you can do that, or you can use powers of 10. Okay, that's fine with me. Okay. 9, number 9. I mean, did you guys, how'd you do on that one? Everybody be able to get number 9? The work is equal to the weight of the object. Did you guys get that? So far, so good?
Yeah, because we would be the same formula the book had, which is F and E to
No,
E.
not.
EXT equals W.
Oh, sorry,
You just
Right.
kind of plug them in.
Yep. But to do it my way, I just said it this way, that
You got
it's
5
either
points.
asking for the weight. Remember, I had on one of the slides that I gave you guys, I pointed out that the weight.
Yeah, you multiply
Sorry,
20
because
times
it's bright,
5.
very dark. Weight equals the mass times gravity, the acceleration
How do
of
you get
gravity.
5.1? That would be 10.
And the acceleration of gravity is actually not always, it's always, I'm sure, 9.8. But in my class, if you want, you can just make this 10. All right, and use the number 10 instead.
So that's why you're going to
Okay?
the others.
But that's how you do that one.
Okay.
It's not very good. Okay, what about, now, number 11.
We haven't done that.
Well, all right, number 11.
.9 times 10 but they got 5 times 10 to the negative 7.
We are, as I said before. Okay, so number
Y'all have
11.
close to mine. I went the other way.
Exerts a horizontal force of 50 newtons on a gurney with a base. Well, isn't this very similar to the one that we did? Didn't I do this in class? I did this in class, didn't I? Why are we doing it again?
Would that be the same one?
Yeah, isn't it the same one?
Which one?
Sure, look at the, I don't have the one here, but, I was not sure. I'm not just, yeah, example 3.2 in the book. It's very similar to that example, right? But you want to go through it anyway? Okay, sure. But it's very similar to example 3.2.
11.
So, where are we? 11. Orally exerts a horizontal force of 50 newtons on a gurney patient. The gurney patient have a total mass of 90 kilograms. So, okay. So you know what you've got here.
Oh, there's an 11 on here, so why are we doing that?
Okay. So we have here the orderly, right, pushing this, going to be pushing this gurney with the patient on it. Then we just put the numbers in. I always write these things down, and I would encourage you guys to do the same. Make a little sketch so you can see what's going on, okay? So in this case, the orderly exerts a force of 50 newtons, all right? So he's pushing, we have here a force equal to 50 newtons. So they're telling you that, and then they're telling you that the gurney and the patient have a mass of 90 kilograms. So here, this mass is 90 kilograms, okay? But, okay, we'll just leave it at 90 kilograms for now. And then it says, if the gurney and the patient accelerate at 0.35 meters per second squared. So now they're telling you that the result of this force is that you have an acceleration of 0.35. All right, you know, I don't hold you guys to units here, but it's going to be 0.35 meters per second squared. What is the magnitude of the frictional force? Okay. So you say, well, wait a minute. What are they talking about? He's pushing with a force of 50. Okay? So if he's pushing with a force of 50, then you guys know from the earlier problems that you did, right? Didn't you write down that the force equals the mass times the acceleration? And that's how the two are related, right? So if I put the numbers in here, he's pushing this gurney, which has a mass of 90. We have an acceleration of 0.35. All right, and the force they say is 50. Does that work out mathematically? Let's see. Of course, you guys haven't done the problem, so I shouldn't ask that question. We should just work it out together. Well, according to the magic calculator here, 90 multiplied by 0.35
31.5.
gives you what?
31.5.
Over 50,
Not 50. What happened? This only gave you 31 and a half. Not 50. But now you know he was pushing, or she was pushing, with 50. Where did the other energy go?
Friction.
Friction! You guys are so smart. That's great. That's where it got lost. So that means that this amount of, only a part of the force that's being exerted is going to be due to the orderly actually pushing. The rest of it is going to get lost due to friction. So the question they ask you is, what is the magnitude of the frictional force? Well, you could say, well, he's pushing with 50. We know now that 31 and a half, I probably should do it that way, all right, is what he's actually moving these two at. So that means that the frictional force must be, what, 31 to 49?
18.5.
18.5. That's the answer. Done. Now, let's stop for a minute. Did you follow that? Okay? That is not a question on the test. But, all right, but I want to make sure you understand, all right, what went on there. Okay? You knew that there was a certain amount of force that was being used, right? But it all didn't go into Newton's second law here because friction sucked away some of that force, okay, and burned it up in friction, right? That converted to heat, for example, in friction. Okay? So that's a little complicated problem. I wish I had assigned that to you. That's one I'd like you to sweat over a little bit or write to me and say, what the hell's going on? I can't figure it. That's okay. Then I would have told you this over the internet. But I'm sorry I didn't do that one. But I just want to make sure you guys understand it, okay? As I say, I don't have one, I don't believe I have one like that on the test. Do I? Well, anyway, I don't have one like that on the test. But I do have ones where there's friction involved. One of the other things that we talked about, and this is probably where how you guys got to figure some of this out so quickly, is that I told you if your car is going with cruise control and you're going, say, 50 miles an hour on a straight road, right, you guys realize then that all your gasoline is being used to fight friction, right? In other words, whatever force the car is pushing with, okay, that's the same amount of force the frictional force is in the other direction. Because when the two forces are equal and opposite, you move at a constant speed. Okay, so someone on an airplane once, somebody said, oh, the airplane, when we're flying at our cruising altitude and cruising speed, it's got something like 450 million pounds of thrust. Wow, that's a lot of power. How much frictional force do you think the plane has to overcome? 450 million pounds of force in the other direction. Because if the plane's going at a constant speed, the two things cancel each other out. Okay? Okay. So that's 11. What's next? No, we're not going to do 21. No, because I decided to skip some of that. Just like, I mean, I learned too, that I know what makes you guys crazy, at least some of the things that make you crazy. So that's why I skipped chapter 2 altogether.
Can you do 23?
Sure.
We didn't have to.
Oh, no, we didn't have to do that, no.
33.
33? All right. Since we do 33, all right. Some of you had a little trouble with 33? Who got 33 right?
Yeah, I'm just going to skip 31 and 33.
Okay. I messed that one up.
was just
let's do this
multiplying.
together. What forces each of the 4 legs of a uniform bed of mass 45 kilograms of dirt on the floor? All right, well, you guys, that's 4 legs, okay? So you know that the mass that we're looking at here is 45 kilograms, if I remember right.
Mm-hmm.
Okay, 45 kilograms. So that means, now you can do this 2 ways. You can convert that to the weight and then divide it by 4. Or you can divide this by 4 and then take one of those numbers and multiply it by gravity. I mean, you can do it either way. All right, so, and I don't know if I mentioned this to you or not before, but I want you guys to always do math the way that works for you, okay? I can follow it, okay, but I want you to do the system you're most comfortable with. So some people would say, well, let's see, it's 45 kilograms, and we're going to divide that by 4 because there's 4 legs there. So that comes out to be what, that comes out to be 11 points.
25.
Sorry?
11.25.
25? Oh, you guys are good. Okay, kilograms. And then if I multiply that by 10, I'll now have the weight that foot has to support. So it'll be 112 and a half newtons. Okay, is what it would
So
be.
we don't do 9.8, we do 10 instead?
I like to cheat, yeah, so I'd like to do 10. No, I just want to make it easier for you. You can do it either way, all right? If you're more comfortable, because calculators make this so much easier. You can just punch in 9.8 and then that's fine.
What do we use in the test?
Either one.
That's open answer?
Yep. Yeah, either answer is good. So in this case, it would be, well, you know, but you see, if you use 9.8, then it would be 11.25, and you would multiply that by 9.8, and what is that? What is that?
110.25.
Okay, 110.25. So when you have the test, if you had something like this on the test, from my answer key, I'll have both answers. All right, so either one will work, you know, if you do that. But the other way you could have done this is you could have said, well, how much does this bed weigh? Well, it weighs 45 times 10, or 450 newtons, if I'm going to use the 10. And then I just divide that by 4, right? And that's going to give me what? 100 and, what did you tell me? It was 112? Right, 112.5 newtons. You're going to get the same answer no matter which way you do it, and I don't care, okay? Whichever way works better for you. If you want to just look at what 1 is, or if you want to look at the whole thing and then divide it by 4, that's okay. Either way. Okay, that one. What's next? 35. How much torque do you exert if you push perpendicular on a door with a force of 30 newtons and a distance of 0.85 from the hinges? Did everybody get that one? Yes? No? Yes, you all could?
You just go backwards, correct?
Well, remember, the formula that you're going to use is that the torque is going to equal the force multiplied by that, what they call that lever arm. That's the formula. So on this one, they're telling you that the torque, they're not asking for the torque. They're saying you push on the
They
door.
gave you the force, they gave you the...
Right, and it's in the right unit, so it's just going to be 30 times 0.85. Okay, do you guys see that? It's going to be 30, and this is just 0.85, and that's it. You can be given this backwards by saying, how much force do you have to exert? Let's do it differently. Suppose I were to ask you, how much force would you have to exert if it's going to take, let's say, 200 units of torque to open the door, and you're going to push, this at a distance of, I don't know, let's say half a meter out. Right? If I were to ask you that, how much force do you have to use? I want you to see it's the same formula. It's just now you would just divide both sides here by whatever that number is. All right, and you would get the amount of force. You see that? So that's another way to use the same formula. Okay? They didn't ask you that.
I'm sorry, so it's just force times the distance of the arm?
Yep.
Okay.
Yep, but this is the distance here.
Right.
In this case, the hinge is right here, okay? And so, you can push it here, and you'll have to exert more force than if you push it over here. It's easier the further out you go. But you guys know that from experience going into malls and things. You always push it hard, farthest away from the hinge. Yeah. Okay. What about 37? Well, 37,
I just wanted you guys to see in that, where they have that little picture. Okay, in the first picture, the only thing that's pulling on the patient's leg here is this one weight. What is it, kilogram? 10. So it's going to be like 100 newtons, 10 times that, or that's going to be the weight pulling down, or 10 kilograms. But in this case, the second case, you have two things pulling. You have the 10 kilograms pulling down, but you also have 10 kilograms being supplied by the ceiling. And you see they're both pulling with 10 now on that foot. That's the only thing they wanted to show you there. Does it make sense to everybody? Is that
Well,
okay?
how would you do that problem though?
Well, what do they say? It says, what force is applied by each traction setup? Well, in the one case, the force is going to be, in A, it's going to be 10 kilograms times 9.8 or times 10. And in the second one, it's going to be 10 kilograms, but like they show you there, you have the same tension on either side. Remember, if you didn't have the same tension on either side of that pulley, then the weight would have to move. Okay, so but it's in equilibrium.
So in B basically cancels itself out?
So it would, no, double.
So we have
It will
to-
double, yes. Okay with that? Okay. You guys get that? Nothing like that on the test, don't worry. No drawings. No drawings on it. Okay. What about 41? You guys, we do 41? Really? We didn't do 41?
Yeah, but you said not to do it. You said I'm doing 45.
Oh, yeah, we have
45. Did you guys try 41?
Yes.
That's a little more complicated in the sense of understanding torque. Okay, well, I should have done the formula, I guess. That's a little more complicated. Okay, you've got a person, you have a lady here doing push-ups, and how do you get into a lady? Don't most girls do it on their knees? No. When I was in school, they did. Now, now we've got women that are seals, right, and everything. It's wonderful. I mean, I think it's great. But, okay, I don't know why he made it a rule here. And this was back in a long time ago. When was this? Printed back in, I guess I messed the tape.
Yeah, this book was in the 80s or something, right?
I wasn't listening to
It must be. Is it 86? Yeah, wow.
Yeah.
Way ahead of its time. Oh, my God, great. No, that was in the 60s. They had already burned their bras. That's right. They did. Oh, my God. Hey. Those were fun years. I have to tell you. They were good years. Burning my registration. Oh, man. But anyway, long time. Times were very different. Let's see. Okay. Now, you look at that picture and you say, well, wait a minute. How is that? How can I reduce that to something that's that is simpler and is more like the door and the hinges here? And the thing you have to think about is, because you've all done push-ups, right? The thing is, when she pushes up with her hands, all right, she's going to rotate about what point? Where's her body going to rotate? Do we have to do it?
Up.
You guys going to make me do a push-up? Is that what you're trying to do?
Push-ups,
No, but where are you rotating? Where's the point? Like, where's the hinge?
And your shoulder.
Hips.
Your hips are
Guys,
Your heel.
remember, when you're doing the push-up, right, what's the rotation point when you do that? Your toes, right?
Oh, toes.
Aren't you rotating about your toes? Right? The toes aren't moving, but the whole rest of the body's moving. So, in this case, you could say, well, I have here like a board that's going to rotate about this point. And the forces that are on it, they have just two. They have her weight, 50 kilograms, about in the middle. So coming down here, we have 50 kilograms.
And pushing up, they don't tell you. They just say it's a force. Pushing up so she can do the push-up this way. And there's your torques. You have 2 torques in this problem. Now the distance is 0.9 and 1.5. So this is 0.9 here. And to go to where her hands are is 1.5 meters. So there's your torques, and they're about the feet, the balls of the feet. So in that case, you would say, well, the torques that are clockwise are going to have to equal, she's holding herself up in this picture, must equal the torques counterclockwise. So in this case, the clockwise one is this one, and the force is going to be 50 times 10, or 9.8, times its distance from the point of rotation, which is 0.9. And now that has to equal her force on the other side, which is just going to be her force times 1.5. So you divide both sides by 1.5, and you're done. Because they cancel over here. Okay, do you see that? You want a problem like that on the test? No. Okay. But I want you to understand what's happening here. The torques, when you're balancing yourself, have to be equal and opposite, or else you fall down. Okay, they have to be. So whatever the torque is pulling down from her middle here, her center of gravity pulling down, she has to exert the exact opposite torque in the other direction. Not the same amount, but just a different number. So what's it come out to be? 500, 450, what is that? Sorry? 294. Okay. 294, whereas this one is, 450. You can see it's less force. But again, she's farther from the point of rotation, so it would be a smaller force, right? Like we were talking about pushing the door. Okay. Okay, so you know how to make a torque calculation, like we're pushing on the door, not necessarily this one, but like pushing on the door. We talked about friction. You guys know the difference between mass and weight, and we talked about that. I'll think of some other things as we go along here. And use that formula, force equals mass times acceleration. Okay, let's do chapter. And yeah, that's all I have. We good? This is chapter 4, and the important thing is that energy can change from one form to another without any loss or gain. All right. In other words, whatever amount of energy you start off with in a system, that's how much you've got. Okay? Now, it can't be lost, but it can be transformed. Okay? For example, like we were talking about the car going up the road at a constant velocity. Okay? And how all the gas is now being used to fight friction. Well, the thing is, all that chemical energy that's in the gasoline that you're burning is all being used to convert to fight friction. So the energy is not lost. It's lost to the car because it's gone. You burn the gas is gone. Okay, you've lost the energy that was in that gasoline, the chemical energy, but you used it by fighting friction. For example. Okay, but now going back to the more basics here. Work is one way to change energy from one form to another, but here's a little bit of a catch. In physical science, all right, work has a very narrow definition. Narrow meaning work is equal to the force that you exert multiplied by the distance that something is moved. So, for example, I can push on this wall all I want, and you guys know that by pushing on here, I'm doing work, I'm burning up calories, right, by pushing on that. But according to that, no work, because the wall didn't move. Okay?
So you need a force, but then you also need the object to move. And the product of those two things, the force times the distance that it moves, that is the amount of work that you do. Okay, now we'll find out, you'll see a little bit later, we get in another 5 or 10 slides, you guys will see how this work is actually just a form of transferring energy from one thing to another. Like if I did move the wall here, if this moved forward, I was pushing a heavy box, then the chemical energy in my body would be used to actually do work. And you could calculate how much that work is by figuring out what is the force that I'm pushing with and how far did I move the object. That would be the amount of work that was done and also the amount of energy that was used. Okay, then, so along with that definition, if you're stretching a bow, okay, the work that you're doing in stretching that bow is that it's being converted into the elastic energy in the bow, right? Does that make sense to everybody? That's what's happening when you pull that? I used to have a little example of that, but I didn't bring it with me. I'll bring it next time. But when you pull, what's happening is you're doing the work to pull the bowstring back, but that work is being converted into stored energy in that bow, okay? Because when you let go of that string, that bow is going to then go back to its original shape, okay? And when it does that, it's going to convert that energy to something else. For example, the arrow. That's probably a better way to put it. You have the arrow in the bow. You pull the string back. You're doing the work, but now your work is being transformed into the elastic energy in the bow. Then when you let go of the bowstring, that elastic energy in the bow pushes the arrow forward and converts the energy in the bow now to the energy of motion of the arrow, which we'll talk about a little bit later. But I just want you to see how energy transfers. For example, like I say here, holding the bowstring, if you're holding it like this, no work is done. Like me pushing on the wall. This is work, but once you hold it, your work is done. So, which is not true. All right, but in terms of physical science, that's that narrow definition. If you're at a stoplight, okay, and the light turns green, right, and you step on the accelerator of your car, right, now your car is built to convert the chemical energy that's in the gasoline, or if you have an electric car, the electrical energy in the battery, but it converts that into mechanical motion. And then that mechanical motion converts to the motion of the car moving forward. So you're getting a direct transfer from the energy that's in the gasoline to the motion of the car going forward. And now since you're in Fort Myers, you only go about 1 block and you get another red light, right? So what happens now is you step on the brake. But when you step on the brake, you guys know how brakes work. You have little pads that clamp onto a rotor, okay? Now that's going to bring your car to a stop by stopping the wheels. But when it does that, what does the energy now get transferred to? What does it become? Heat, right? Heat energy. So you see, you started off with potential energy and that gasoline that contained that energy. That got converted to mechanical energy that moved the car and gave it the energy of motion. And then you stepped on the brake, and then that same energy got converted to heat and in effect got lost. Lost in the sense of us being able to use it. Didn't get lost in reality. It's still there. It's just now we've warmed the air up a little bit by hitting the brakes. But I just want you to see how energy just transfers from one form to another. A weightlifter lifting weights, all right, they do work against gravity, but if they hold the weight up, no work. You do push-ups, you're doing work against your own weight, but if you hold yourself up, you're not doing any work, and that's just because the distance is zero. If you always remember that the work has to be the force times the distance, and if the distance is zero, there ain't no work that's being done in this sense, in this narrow definition. The unit for work and energy is the joule, J-O-U-L-E. You'll see it in your book as a capital J, the way it's written, named after a scientist, of course. So as it says here, if you lift a 10-kilogram box, you lift it up 1 meter,
Okay, you're lifting up the weight of the box, so it's 10 kilograms times gravity. That's the weight of the box, multiplied by the height in meters that you've lifted it. So you have then just done 100 joules of work. But if you hold it there, now you're not doing any work, okay? Which I know doesn't make sense, but actually it works out in terms of the, conceptually and with mathematically, it works out to be, that's correct in physical science. But you know, of course, that if you have to hold something up that weighs, about 100 newtons, you're going to have to, 10 kilograms is about 25 pounds, so you're 23 pounds, so it's going to be, holding it up, you're going to have to do some work on that. But as I say, that's in reality as opposed to in this narrower definition. Okay, we're going to come back to this in a minute. Well, here's another example. This is out of your book, example 4.1. Let's take a look at that to make sure I've got that right. It's not 4.1 in the other class. Pretty sure it isn't.
It's 4.1.
It is. So this, where are you here? 4.1. Calculate the work done by an ambulance attendant who pushes a patient on a gurney with a horizontal force of 25 newtons for a distance of 3 meters. Okay. Work is the force times the distance. Right? You guys can do that? That makes sense? Good. Now the next example, it says, how much work is done lifting a 10 kilogram sack of groceries 1.2 meters from the floor to the table? Okay, well now, you're lifting it, again, you got to think about this. It's 10 kilograms, so you can get the weight by multiplying that by 9.8 or 10, right? But then the distance you're raising it is at 1.2 meters, so the amount of work done is going to be the weight times the distance that you lifted it. Okay, does this make sense to everybody? You okay with this so far? Reminds me of something that's not in the chapter here, but a problem that, did you ever notice, do any of you guys fish? I mean, some of you guys do some fishing. Did you ever notice if you're trying to get the fish, you want to get it up onto, if you're on a fishing off a bridge or if you're in a boat or something, you want to lift the fish up. I think you guys know, probably from experience, that when you get the fish near the top of the water, you just gently lift the fish up and put it in the boat. Because if you don't, because this is like lifting something real gently, if you don't lift it gently, if you jerk it to get it in the boat, now your line has two forces that that it has to contend with. The weight of the fish, and you jerking on that weight. Remember Newton's second law, force equals mass times acceleration. If you're accelerating the fish upward, you are now creating another force in that line, and so you can snap your line that way. Or you could just use heavier line and don't worry about it, just yank it, bring the fish in. But I just wanted to point out to you that there's another force there. But anyway, let's get back. This just reminded me of that. How when you do lift something up quickly, remember you're accelerating it, so you're generating another force. Okay, when you do that. But okay, so I think we're okay with that. Now, power. And we're going to do a lab on this. Those of you that have a lab, we're going to do a lab on work and power this week. But power is the amount of work that you do, but divided by how long it took you to do it. In other words, the faster you do the work, the more power you're going to have said to have expended. So it's always going to be the amount of work that you do divided by the time to do it. The work will be in joules and the time will be in seconds. Okay, we'll do, as I say, a lab on this. And the unit for power in this international system is the watt. You know, in our country we're sort of schizophrenic because we have some British units and we have some international units. But this is an international unit. The watt is a unit of power. But anyway, I have a slide that shows you what this means about this, how this power can be different. How much power do you need if you want to do 500 joules of work, but you do it in 2 seconds, then the amount of power
that you have expended is going to be 250 watts of power. But if you took 5 seconds to do it, now you're dividing by 5, so the power is going to be a lower number, and so forth. You can, you know, the longer it takes you to do it, the less power you're developing. But the amount of work is the same. That hasn't changed. It's still 500 all the way. But it's just, do you do it quickly or do you do it slowly? Okay? When you do it quickly, you're said to be using up more power, or you're expending more power because you're converting that work into something else very quickly. You're converting something with the work. All right, so power is measured in watts, and you guys know that. We have you have kilowatt hours, right, for our actually. You guys have electric bills you have to pay, right? You have kilowatt hours, right? That's the unit. They have kilowatt hours, all right? Is what your bill is in, and that's what you pay for. Something like I don't know, something like about 8 cents per kilowatt hour, or something like that. It's FP&L, or well, that's the most common one down here.
We have LCEC.
I was going to say the co-op. It's another one. But it's still roughly about 8 cents. But now I want you to notice something here. Look at the units of power. You see, the power we said was the watt, right? And the watt is going to be equal to the energy divided by the time. So if I put that here, energy divided by the time. Okay? That's not what this tells me. What this tells you is kilo just means 1,000. So this is really watts multiplied by hours, or time. Not seconds, but hours. Okay? You see what they did here? If I multiply both sides by time, here, if I do that, then the time will cancel on this side. What you're being billed for has nothing to do with power. It has to do with energy. That's all FP&L cares about. How much electrical energy did you take from them? That's what they care about. So that's why your bill is in kilowatt hours, because you're paying for how much electrical energy. Just like when you're going to the gas station, you're going to pay that $1.70 something per gallon for the chemical energy that's in that Exxon Mobil or whatever kind of gas you use, right? I use Speedy, or Speedway, or what is it, Speedy, I guess, right around the corner here. But in any case, they're charging you for the energy. Just wanted you to realize that. Some people say, that's my electric power bill. No, it's not. That's the energy bill. Do you think Exxon Mobil cares how fast or how slow you use their gasoline? They don't care. They just know every time you need a gallon, man, you're going to pay $1.75 or whatever it is for that. Okay? They don't care. If you run a car that burns up the road and gets 10 miles to the gallon, and you know, fine. They don't care. You'll just be coming back to see them sooner. That's where the power comes in, how quickly you use up the energy in that gasoline. But the same thing, I just wanted to point out to you, what you're paying for from FP&L or the Lee County, the co-op, electric co-op, that is, what they're charging for is the electrical energy. The power is determined by you. You want to leave all your lights on, you know, run the TV all day and all night, run the oven, run the dryer, whatever you want to do. That's your business. They don't care. All they care about is how much energy did you take from me, and I'm going to charge you for that. So anyway, it's a little aside, but I thought I might give you a little more insight into this. Okay, now, mechanical energy of a system, whatever it might be, it could be a car, it could be a person, you know, it could be anything like that. The system, mechanical energy refers to the energy. We're going to just talk about potential energy, like gasoline has chemical potential energy, that bow had elastic potential energy, but we're going to stick with gravitational potential energy. In other words, you lift something up like this, you have just now given it gravitational potential energy, because if I drop it, it will come back down and could do some work for me, turn something on, for example. And the other energy is energy due to motion. And the sum of those two things, the potential and the kinetic energy, that's what we call the mechanical energy of a system. So potential energy is related to the height that you raise something, and the kinetic energy is related to how fast something is moving. And before I give you an example, let me just point out some other things here. Different types of potential energy. This is the one we're going to talk about the most. But here's some examples. The water that's in the water towers that we have. We have, what, about a half a dozen water towers around Fort Myers, and they filled them up in the middle of the night. I remember taking a shower one night. I had no water pressure. Man, it was almost nothing coming out. And I called the water company the next day. I said, "What's going on?" He said, "Oh, we fill those water towers, between midnight and 4 a.m., so, sleep later. You'll have water pressure." He said, "But it really only drops about 10 psi. But in any case, that's what we have. Why we have the water up there, because then it's easier to control using gravity the force of that water, the pressure when it comes down from the water tower. Pile driver, okay, it's hammering a piling into the ground, for example. That's using gravity. The engine lifts up that heavy weight and then lets it go. Bang! It comes down. It uses gravity to generate the energy. And in general, it's going to be any object above some reference level. I'll show you what I mean by that in a minute. Chemical potential energy we talked about, like in gasoline. Elastic potential energy, like in a rubber band or a slingshot or a bow and so forth. I just want to give you some examples. But this is the one that we're going to just focus on in the course. Now, here's the thing. This formula for the gravitational potential energy is exactly the same formula that we just had for work. It's the weight times the height. Done. And the answer is in joules. Remember, all energy is going to be in joules. So, you want to lift something that's 10 kilograms up 1 meter? Well, the potential energy is then going to be the mass times gravity times the height. Or the mass times gravity is, of course, the weight times the height. Okay, so it's really the same formula that we had for work. Okay, the work you were doing lifting something up, for example. Okay, you guys okay with that so far? It's the same formula. It's just now, instead of pushing a crate across the floor where you exert a force and you push it a distance, in this case, when you're dealing with gravity, you're lifting it up, you're raising it again, so you're going against gravity to lift it. You're doing work in that sense. Okay, and then here's another example. Well, this is the example in your book. Didn't we do this one? We did that, didn't we already? Yeah, person lifting a sack of groceries. Okay, well, it's the same, except now, instead of being work, all right, I wanted you to see the same problem in terms of potential energy. You have, by lifting that up, you have given it a certain amount of potential energy. All right, but it's still the same formula. It's going to be the weight multiplied by the distance that you raise it. How about this one, 4.6? And that one says, calculate the work done by a 50-kilogram nurse lifting a 25-kilogram child a half a meter onto a table. So in the figure, what they wanted to show you here, it's on the next page, that the nurse is, she's a smart nurse. Right? She knows how to flex her knees when she's picking something up. She doesn't just lean over, pick it up. She flexes her knees, so her center of gravity is going to come up the same distance that the child that she's picking up is going to come up. So in this case, all right, her 50 kilograms has to go up the same distance that the child is going up. The child is 25 kilograms. So what is the work that she does? She does the work in, first of all, getting herself up, right, moving that center of gravity up. She has to move up. And then she also has to do work against the gravity with the child. So she's gaining potential energy with both of those things. Now, is that okay? Think about that for a minute. Does that make sense? Mm-hmm. I want to make sure you guys are okay with that it's, all right, because these energy things can be confusing. I wanted you to see, I'm not sure how your book explains it, but it's probably very similar. I think they do it in a shorter form. But in any case, the total work done by the nurse is going to be lifting herself up. You guys know that. If you ever exercise and you do squats, right? You know that that works, right? That works you out when you do that because you're moving your center of gravity up and down, right? So you're going with gravity and then against gravity. So you're doing work every time you do that. But in this case, she's also lifting up a child. You okay with that? And then, the last energy we'll talk about is kinetic energy. And kinetic energy, the energy of motion, it comes from the Greek word for motion, kinetic or kinesis. And it is always the same. It's 1/2 the mass of the object times the speed of the object squared. That's the one formula that we have. And the work done is always going to be, if an object is moving and you're changing its speed, you're going to have to do work. Now remember, if the object moves at a steady speed, then that means that there's no net force on it. And if you want to speed it up or you want to slow it down, all right, you have to do work in order to have that change. So that's why down here it just says whatever work you have to do, it's always going to be how much kinetic energy did you have at the end minus how much kinetic energy did you start with. It's always going to be that difference between those. That will equal then the work that's done. We have an example of that, maybe not. Well, this explains it in a little bit more detail. It just says the energy changes whenever work is done. If you have an initial amount of kinetic energy and then you do work to increase the object's speed, like you step on the gas pedal, all right, then you're going to have a greater amount of kinetic energy because that speed is going to be, the v squared is going to be now a bigger number, the velocity squared. Or if you step on the brake, you're going to have a certain amount of kinetic energy you're starting with, but then you're going to decrease the object's speed, so you're going to lessen the amount of kinetic energy. So this is why they say in summary, the work done equals the change, this triangle means change in, or difference between, change in kinetic energy. It's called the work energy theorem, is what they call it. All right, so now I've talked about all the energies and, well, your book does have an example, 4.5, where they combine the work formula and kinetic energy formula. Where is that? 4.5. Go back to it. It says, a pitcher throwing a fastball steps forward in the manner shown in the figure. So he's able to exert a force on the baseball over a large distance, giving it the greatest possible speed. Calculate the speed of the baseball if it leaves his hand when the pitcher exerts an average force of 200 newtons over a distance of 2.5 meters on a baseball that weighs a half a kilogram. So what I'm trying to show you here is the arm is moving 2.5 meters, the force is 200 newtons, all right? And so what you have, remember, the work done is the force times the distance, right? So that means that the force times that distance is going to have to equal this. It's going to be 200, right, for the force times the distance of 2.5. All right, that's one number. On the other side, you have the change in kinetic energy. What's your final kinetic energy minus what is your starting? Well, your starting kinetic energy is 0. The ball's in his hand. It's not moving at all. So it's 0. But then he gives it that motion when he moves through. And so your final kinetic energy is the only term that you have over here. So you know how much work was done, and all that work goes into the kinetic energy of the ball. 1/2 mass times the speed squared. So you can look that over and see how, how that works out. But I wanted you to see how that formula would actually be used. You could use it to say, I don't know, if I tell you you're going at 20 meters per second, let's say, in your car, and I give you the mass of the car, and say how much force is going to take your brakes to stop you, and say 50 meters, for example. You would use the same formula. It's just that in that case, your initial speed would be the number here, and your final one would be 0 because you're coming to a stop.
So you would still have your force times the distance that you go equals 1/2 mv squared. So take a look at that in your book when you, and make sure you guys, we'll go over it again next class, all right, before we have any tests, if you guys have any questions about that. Now, I want to show you how, let me just see, I don't think I have any more. Just the conservation of energy, which just says energy can't be created or destroyed. I mentioned that earlier. It just gets changed from one form to another. It moves, like I gave you the example of your car. The energy in the gasoline gets converted to mechanical energy, which moves the car, giving the car kinetic energy. But then you step on the brake, and now we lose that. We don't know. Gosh, you guys would be millionaires. You could figure out a way to use that heat energy from the brakes. That would be great. You know, it wouldn't, instead of just letting it go into the air. You know, it doesn't get lost. It gets lost to us, but it doesn't get lost in terms of the universe or nature. The energy is still there. It's just now warmer air molecules, okay, and hotter pads, okay, and rotor on your car. So energy gets transformed. And I wanted to give you an example here of a pendulum, but I'm thinking an easier way to understand the pendulum is this. Let's say it's a nice sunny day, and you're taking your little niece to the park, and you're walking around with her, and she's running around, and she sees a swing, and she says, "Oh, I want to go on the swing." Would you put me on the swing? You say, "Sure." So you go and you take her, right? You sit her down on the swing, right? She holds on to the ropes or the chains or whatever's there, right? Now, you don't want her to fall off that swing, right? Okay, so the swing, the seat on that swing is going to be as low as she's going to go. Okay, so when she's swinging, so what happens is we'll set your zero of potential energy there. She's not going to go any lower than that. Now, you come up behind her, you grab the ropes or the chains, and then you do work of pulling her back, all right? And when you pull her back, is she staying the same height, by getting higher or getting lower? She's getting higher, right? So you're giving her, your work of pulling her back is giving her potential energy, because that seat now, instead of being down here, the seat might be up here, right? Because you pulled her back. So here's a direct example. You do the work, you've given her potential energy. Now you let her go, all right? Now what happens is, let's say for the sake of argument, you've given her 100 joules, all right? Well, that 100 joules depends on her weight and how high she is from her starting point, that's 0. So as the swing goes down, that potential energy you gave her goes from 190, 87, it goes down to 0. Where'd it go? What did it change into? Kinetic energy. She's moving now, right? So that potential energy got converted to kinetic energy, and so that's what keeps her moving. And in the absence of friction, she'd go right back up to the same height. But of course, you know, with friction, the wind and the whatever, however it's can be, ropes are connected. So you'll lose some energy due to friction. But then she'll come back, and so she'll go and get up here, and it'll be now the kinetic energy will be 0, but the potential energy will be the 100, okay? And now she'll come back down. The potential energy will go to 0, but it becomes all that kinetic energy, which then lets her come back up here. Okay, do you see how that same amount of energy that you expended got transformed? Now, of course, you're going to have to give her a push every so often because of friction. If any of you have a pendulum clock at home, how hard they are to design, you know that? Because every time that pendulum swings, there's a spring in there that gives the pendulum just a tiny push, just to compensate for the friction that's there. That's why it keeps, it keeps swinging. So, but in any case, all right, I just wanted you to see that. I think I have another silly drawing here about, well, this is, before I get to that, I just want to point out, here's another case of you pull the bow back, all right, so your work is going into the elastic energy in the bow, and when you let go of the string, then that elastic energy in the bow gets transferred to the kinetic energy of the arrow. You see how this stuff how this energy just moves? Yes, sir.
Is there a formula for elastic potential energy?
There is, but we're not going to, it's too complicated. Yeah. Well, we could, yes, there is, but no.
I want you just to understand
So we're only going to use
conceptually.
the gravitational.
Correct. Your car, like we were saying before, if your car is using 100, say 80 joules of, if it's moving with 80 joules of kinetic energy, but it loses about 20 joules due to friction, you've got to put in 100 back here. But we saw that in an earlier problem. Remember one of the earlier problems about pushing, the person's pushing with a force of 50 newtons, and here's the acceleration of the gurney and the patient and the mass, and where'd the extra energy go? It's the same idea here. I just wanted to point out to you it's being lost to friction. Okay? So it's not lost to the universe. The energy is still there. It's just that we can't use it, because we don't know how to use that, how to get it back again. Be nice if you went up a hill and you burned gas going up the hill, and then when you came back down, the gas went back into your gas tank. It doesn't work that way, though, does it? Here's what I was thinking before. A person jumps out of a building, all right, they have, if this is the zero of potential energy where they're going to get caught here, all right, they jump out, they start out with all potential energy, but then as they fall, they come down to zero, but their speed, their kinetic energy goes up to 100. But I wanted you to see at every point, it adds up to 100 as you go across. It's just shared. In the one case, the potential energy, gravitational potential energy goes down to zero. The kinetic energy goes from zero up to the starting value of the potential energy. Okay, it's just really how the energy gets transformed from one form to another. And this we're not going to do on the test. I don't have anything like this on the test, but I just wanted you to know what a machine was. It's just something that multiplies force. I don't want you to think, well, let me put it this way. You get a flat tire, all right, and so you're all alone. You got to change this tire. So you get the jack out. It's all in the, it's in the back of the car. The back of the car, you hook it up. Now, how can you lift? How come you can lift maybe 1,500 pounds by yourself? Get that car to come up off the ground so you can change the tire. Say, wait a minute, I can't lift 1,500 pounds. How is this possible? Because the jack transforms that energy into another form. Remember, the work is the force times the distance. When you're pumping the jack, right? You've got the long, the long rod here, and you're pushing it down. You're going through a big distance with maybe a small force, maybe just 50 pounds. Okay, that you're doing. But then on the other side, what happens here, that changes into a big force to push that 1,500 pounds up, it'll be a little distance. Because the product, F times D, has to be the same. I just wanted you to know that's how jacks work. Okay? You're not creating energy anywhere. But what you're doing is because the energy is the force times the distance, I just want you to realize that by making it a bigger force, you'd have to have a smaller distance on the other side. That's all. But that's why when you keep doing this, while you're going through, maybe 2 feet and 2 feet and 2 feet, but the car is only going up, 1/8 of an inch, 1/8 of an inch, because it's got a much bigger force is being applied on the other end. Just for your information.
So on the previous slide, it always inverses?
Yes, because in this case, yeah. Because like here, I don't have any loss of friction. So unless they tell you that there's a frictional loss, then you would assume it stays whole. Yes. So it will always be 100 in that case, in that example. And that's it.